In fields like genetics and predictive medicine, calculating the probability of a specific outcome carries massive physical stakes. Yet in the classroom, we often reduce these highly dynamic systems to dry exercises in algebraic memorization. This approach consistently causes students to fail. They conflate mutually exclusive events with independent ones, or they attempt to calculate union probabilities while entirely forgetting to subtract overlapping sections. Effective probability modeling treats every calculation as a measurement of the geometry of sets. At its foundation, calculating a probability is simply the act of measuring a specific, bounded area within a strictly defined universal space. When you shift from memorizing symbols to visualizing geometric boundaries, the most common errors disappear because the physical structure of the problem prevents them. This rectangle represents our sample space. It is the absolute geometric boundary, where the total probability equals precisely 1. An event is a specifically bounded subset occupying a distinct area within that larger sample space. The probability of event A occurring is the ratio of its specific area compared to the total area of the sample space. Everything residing outside of that specific boundary constitutes the complement. Because the total space equals 1, the area of this negative space maps directly to the rule that the probability of A complement equals 1 minus the probability of A. If we roll a standard die, our sample space is the set of numbers 1 through 6. If event A is rolling an even number, we are simply isolating the 2, 4, and 6 within that fixed area. Every single valid calculation must mathematically start by identifying the absolute borders of this entire sample space first. When we introduce a second event to the system, these geometric boundaries often overlap. The specific area where both events exist simultaneously is the intersection. The total combined area of both events, regardless of whether they overlap, is the union. This creates the inclusion-exclusion trap. If you simply add the area of event A to the area of event B, you are stacking one circle on top of the other, which means the central intersection has been counted twice. To accurately measure the flat plane of the union, we have to mathematically subtract one layer of that double-counted intersection. Probability formulas are not magic rules to memorize, but rather necessary accounting measures to prevent double-counting physical space. We can test the durability of this geometric logic by scaling up to a scenario involving 3 interconnected events. To find the union of A, B, and C, we start by adding all 3 individual base areas together. Because we've stacked multiple sets, we must subtract the 3 two-way intersecting lenses to correct for the overlapping layers. Deleting those lenses creates a new problem. We end up subtracting the exact geometric center where all 3 sets meet one too many times, leaving a mathematical hole in the center of the plane. To complete the calculation, we simply patch the hole by adding that specific 3-way intersection back into the equation. This geometric logic scales universally, removing the need to rote-learn complex expansion formulas. This brings us to the highest friction error in probability, conflating mutually exclusive events with independent events. 2 events are mutually exclusive when they have an absolute physical separation within the sample space. Because there is no overlap, an intersection between the 2 is structurally impossible, making its probability exactly 0. In contrast, independent events are defined by an overlap. Independence is an invisible proportional property. It means the occurrence of one event does not alter the mathematical proportion of the other. The formula P intersect B equals P of A times P of B proves that the ratio of A's area inside B is identical to A's area in the whole space. Success on this topic requires distinguishing between these rigid physical boundaries and invisible mathematical proportions. Conditional probability asks us to calculate an event given that another event has already occurred. The phrasing given B acts as a mathematical instruction to destroy the original sample space. The boundary of event B becomes the new total universe. Within this shrunken universe, the only portion of event A that still exists is the original intersection lens. The conditional probability is the area of that surviving lens divided by the area of the new universe, event B. Ultimately, conditional probability is just a standard calculation that is executed within a newly, drastically shrunken geometric universe. In fields like genetics, sample spaces become too massive to reasonably draw as geometric circles. We use combinatorics, permutations and combinations, to calculate total outcomes when the number of boundaries makes drawing them impossible. Tree diagrams provide an alternative map for sequential events. Multiplying probabilities along these branches calculates the intersection of events. Each path concludes at the same geometric intersection we previously isolated in our diagrams. Trees and combinatorics provide the navigational tools required to map this geometric space when the complexity outstrips our ability to draw circles. The final concept in the system is the expected value for a discrete random variable. Expected value calculates a long-run average by weighting every possible outcome by its precise probability area, acting as the mathematical balancing point of the data. This balancing point relies entirely on the strict boundaries established at the very beginning of our geometric model. Mastering the interaction between these spatial components, unions, intersections, and conditional constraints, unifies the entire IB probability framework. Whenever approaching a complex probability problem, define the boundaries of your sample space universe first, and the calculations will naturally solve themselves.